In this lesson, we're going to take a look at an object moving in a circle. Now, we kind of approached that with a projectile, where we had something that moved in this parabolic path, and we had a force that always acted down, even though the motion was initially in a different direction. And we saw when that happened is the path curved. Well, the next extension of that is curving something all the way around in a circle. So let's look at something moving in a circle. Now, when we say uniform, there's one thing that we have to keep in mind on that. Uniform circular motion means that the object's speed is constant. And when I say speed, I mean however fast it's going here, v, is the same speed that it has any other spot in the circle, v. So usually we think of v as velocity. I'm using the magnitude of velocity for speed. Now, if we think about this object and say it's traveling counterclockwise around the circle, at any instant it does have the same speed, v, but it has a different direction. So the velocity here at the top, or sorry, over here at the side, its velocity is all vertical and it's all up. So if we were keeping track, we'd say it's positive vertical velocity here. But as it traverses this circle, it moves this way, and now its velocity is all in the horizontal direction, and it's negative, it's to the left. And then it comes over here and it's got negative vertical velocity and no horizontal velocity, and then when it reaches the bottom, it's going to have positive horizontal velocity, and that whole thing keeps rotating around. Its direction keeps changing even though its speed isn't changing. So uniform circular motion, constant speed, but the direction always changes. Now, if that's the case, we know it is accelerating. We know Newton's first law says an object's velocity will remain constant unless acted upon by an unbalanced force. And constant velocity means constant speed, constant direction. And this is not a constant direction. And that means the velocity is changing, and that means there's an acceleration. And Newton's second law tells us, well, there must be a force. We'll get to the force part later. For now, let's just concentrate on the acceleration part. What I want to know is which way is that acceleration, right? Because if something is moving up and then it's moving down, I know that it must accelerate against that direction. So just between these two positions, we know that the acceleration must be down. Of course, when it switches back, that acceleration must be up. And between these two positions, first the acceleration must be this way, and then it must be that way. So I've got a constantly changing acceleration as well. But we can make it a little bit easier if we put ourselves in a different frame of reference, right? We pick a frame of reference so that our acceleration is only in one direction. We're going to do that with this as well. Now, to do that, think about a marble rolling along a straight path along the ground. If you wanted that marble to move in a circle, what would you do? Well, if you wanted it to curve along this path, you would give it a push when it was here to the left, and now it's moving this way. And so you would give it another push to the left, and so now it's moving this way. And you would give it another push to the left. And so every time you are giving it a push to the marble's left, well, that means you're constantly pushing that marble in towards the center of the circle that you want it to traverse. And that is actually the same thing that is true of the acceleration of the marble, right? Since forces cause acceleration, and to get that thing to move in that circle, you're always pushing it towards the center. We know then that the acceleration is towards the center. So the object accelerates towards the center. And because of that, we give that acceleration, the acceleration towards the center, its own special name. We call it A sub c, or AC, and that's centripetal, or center pointing acceleration. Okay. So AC is centripetal acceleration. It's centripetal acceleration. It always points along a radius. So if this is the center of the circle, the radius is that distance, and no matter what radius we draw, the acceleration is always along that radius towards the center. So you will also see this called radial acceleration, since it points along a radius. Okay? And in fact, your book uses that. The book uses AR for radial acceleration. I use AC, centripetal acceleration. They are the same thing. Now, we can describe and calculate centripetal acceleration in a couple of different ways. First, we can do it in terms of velocity and radius. And we're going to go through an activity in lab where we derive experimentally the equation centripetal acceleration is equal to the speed squared divided by the radius r. Your book also goes through an explanation on that. To really derive that, we need calculus, and we're not going to do that. But we will go through and do that in the lab. We will come up with this equation. Okay. Now, if you think about what that means, centripetal acceleration is proportional, directly proportional to the square of velocity, and inversely proportional to the radius. Which, if you think about it, if the radius is infinite, then it's not a circle, it's just a straight line, and that makes my acceleration 0, because I have a number divided by infinity, that's 0. I have no centripetal acceleration. Now, if the radius is smaller than that, then we're going to have some centripetal acceleration, but the faster we're moving, the more acceleration there is, which, if you think about your own life experience, is probably true. When you go around a corner at low speed, you don't feel that. And remember, you feel accelerations, you feel changes in motion. When you go around a corner at high speed, there is a bigger acceleration, and you feel it, and you get thrown one way or another in your car. It's the same concept that roller coasters use. They have lots of tight corners and spirals because you get accelerated, and that's fun. You feel that. So centripetal acceleration is equal to v squared over r. But we like to describe uniform circular motion in more than one way. We often describe things in how many revolutions they make. Revolutions per second. Okay? And so you might have heard of RPMs, that's revolutions per minute. Revolutions per second is what we call frequency. Frequency describes how often something occurs, and it's revolutions per second. Now, if we think about what that is, F equals revolutions per second, we can invert that. We can say, well, how long does it take for one revolution, right? So the time for one revolution is called period, and this is equal to seconds per revolution. Okay? Now, what that means is that frequency and period are inverses of each other. So frequency, revolutions per second, period, time for one revolution, and so period is 1 over frequency, or if you would like, frequency is 1 over period. Now we can use this to our advantage to kind of figure out what's going on with centripetal acceleration when we're given frequency as opposed to speed. And it's easier to count revolutions than it is to measure velocity, so a lot of times you'll get this. And so what we know is when something travels in a circle, the distance that it moves is the circumference of the circle. So circumference equals 2 pi r, where r is our radius, right? So if I say that's my distance, and I remember that speed is distance divided by time, the time it takes for one complete revolution is period, so the circumference divided by period is 2 pi r over t. Now we do use capital T for that time, the time for the period of revolution, and that gets us this equation. The speed is equal to 2 pi r over period. But 1 over t, right, I could rewrite this as 1 over t times 2 pi r, is equal to frequency. So what we get is velocity is frequency times 2 pi r. And so we can use that equation as well to help us determine the centripetal acceleration, which if we put into this equation, AC equals v squared over r, we can put in 2 pi rf for v, we have to square it, over r. Now, be careful with this because there is some simplification we can do. So I can say AC equals, and 2 squared is 4, pi squared is pi squared, r squared is r squared, and f is squared is f squared, right? I just squared everything in that and divide by r. Well, that means I can actually cancel one of those r's, and so I do get centripetal acceleration is equal to 4 pi squared r f squared over 1, or just this equation. Okay, so now we have two equations for centripetal acceleration, one that relies only on the velocity and the radius, and one that relies on the frequency and the radius. And of course, because we're relating that back to the circumference, there's some pi in there as well.